Okay, hello. So this video lecture is about cross-validation and the standard errors around the cross-validation curve. How do we calculate them? Where are they coming from? Okay, so when we are doing regularized regression or lasso regularized regression, we have typically a sequence of lambdas from small to large, and there are let's say there are n lambda of them, and then we put them into this vector lambda. Let's, for example, for ridge, okay. And imagine we are doing k-fold cross-validation. We have n observations. We have n lambdas, n lambda. So each column of this E ridge matrix corresponds to one of these lambdas. First fold, second fold, third fold, fold k. Okay. Now what we do is we take fold I, the ith fold becomes X validation, Y validation, and everything but the ith fold becomes the training, becomes X train and Y train. And then we solve a ridge regularized problem using the training data, Y train and X train. So we call elNet in R, and then we can get the betas, and the betas, the A ridge beta, essentially the beta coefficients of our elNet object will be a matrix, okay. Will be a matrix. So the beta coefficient of our elNet object will be a matrix with p rows and n lambda columns. Remember, n lambda because we have n lambda lambdas. And the way it's organized, it's from the small lambda. Let me remember which one was the small, which one was the large. Yeah, lambda 1 was the smaller, and then lambda 2 to lambda n lambda. The first column gives us the first estimated beta. The second column gives us the second estimated beta corresponding to the second lambda. The third column gives us the beta coefficients corresponding to the third lambda. Okay, so we have this matrix, and each column refers to the estimated coefficients corresponding to the lambda. Okay. Now, what we are going to do is we are going to call them in reverse order. In reverse order. So we want the beta with the smallest lambda to be the first column. The beta with the second to smallest lambda to be the second column. That's what we are doing here. And then we make this as a matrix. And let's call this ridge beta. Okay. So this will be beta hat for lambda 1, beta hat for lambda 2, beta hat for lambda 3, beta hat for lambda n lambda. Okay, so that's all we're doing. We're just manipulating the data in the form that's going to be useful. In a second, you will know why. Okay. So when we're doing k-fold cross-validation, we have this vector y, which consists of n observations, and we want to do k-folds, so we have k-folds, and the indexes of the kth fold, okay, so if k is 1, then k minus 1 is 0, 0 times d is 0, so it starts from 1, we will do 1. K is 1, d, so 1 to d. D is the size of each fold. D is the size, is the number of observations within each fold. So this is 1 to d. Then we have here d plus 1 to 2d. Then we have 2d plus 1 to 3d. And then here we have 1 plus k minus 1d to kd. That's where the indexes come of this vector y. This is where the indices of this vector y in k-fold cross-validation comes from. Okay, so we take what is here, put it aside, use the rest to train, and then we test it on this. So this part and this part together make y train, and the rest becomes y validation. And the same thing we do with x. The part for x validation, we take it out, it becomes x validation, and these two parts together make our x train. Again, the number of observations in each fold is d. Here we have p predictors, so it's p times d. Okay, and then how do we get a prediction for the validation set? We just multiply the ridge beta. Remember, the ridge beta is a matrix where each column corresponds to one of the lambdas. So when you multiply it by x validation, you will have a matrix where each column is x val, the first beta, the beta corresponding to the first lambda. Then, so here you have the prediction for the validation data set for lambda 1. And then here you have it for lambda 2. And then here you have it for lambda n lambda. And then when you subtract the y hat ridge minus x val, because this is y hat ridge, so this is the matrix which has in it the prediction values for the x val for all the lambdas. And then when you subtract y val, then in the first column you have x val beta hat lambda 1 minus y val. In the second column you have x hat val times beta hat lambda. So this is the residual, this is the vector of residuals for the validation data set when you use a ridge model with lambda 1. This is the residuals you will get for the prediction on the validation data set when you use lambda 2 and then you go to lambda n. So this matrix has d rows because this is for the validation set. The validation set includes one fold and the size of each fold is d, and the number of lambdas we have is n lambda. So this is our E ridge. Okay. And then E ridge, what is E ridge? Is a concatenation of all these residual vectors. Okay, so E ridge, so this residual vector has d rows, n lambda columns. E ridge has n lambda columns, n rows. And how do we calculate E ridge? This is the kth fold, and this part is this. So this is first column, second column, n lambda column, and this piece here is nothing but what we have here. So residual for the validation data set for lambda 1, lambda 2 to lambda n for this part. And this goes in here. So once we have this, we have a set of residuals for each lambda. We have n residuals for each lambda. We have lambda 1, lambda 2, lambda 3, lambda j, lambda n lambda. We have n residuals, so we use these residuals we can average them. Actually, these residuals, we need to square them to get the e's. The e's are the errors. Okay, e is the square of the residuals, and then we average them, and then we have the k-fold CV error for that specific lambda, and that gives us the average of the squared residuals. And then if we calculate the standard deviation of this, then divided by the square root of n, because we have n of them, we get the standard error. And how can you do that in R? Well, what is the standard deviation here? What I mean is take each of these errors, which the error here is the squared error again. This is the squared error. We can use this line of code. Apply E2 means apply to each column the mean. And then you apply standard deviation, you get the standard deviation. So this E ridge And E lasso that we create are the squares. So what I said here, just remember. Sorry, this doesn't have anything to do with this. These are the squares. Okay. So I hope this clarifies everything regarding this problem.